Okay, a review of the mean and standard deviation. The mean of a distribution is a measure. Basically, it's a numerical measure that's used to describe the center of the distribution. The standard deviation is a measure, another numerical measure that helps describe the spread of the data values within the distribution. In this section, we'll use techniques to help interpret the spread of data values within the distribution. So are they spread out or are they close together? And if they're spread out, how far spread out? If they're close together, how close together are they? The standard deviation as a numerical measure measures just that. Okay, the empirical rule is a rule we're going to apply, but it only applies for distributions that are approximately bell-shaped, not skewed distributions. There are three parts to this rule. If we look at a bell-shaped curve, approximately 68% of the data values will lie within one standard deviation of the mean. So here's our bell-shaped curve. If we look at the horizontal axis, we put x bar right in the center because the mean is right in the center of the bell. And then on either side, we can add a standard deviation and subtract a standard deviation, just like we did with that previous example. And the rule says that 68% of the data values in our distribution, in our data set, are going to fall within that range. Now again, this only applies to bell-shaped distributions, so you have to be told ahead of time that the data set you are working with is approximately bell-shaped. So if we shade in that area, that 68% of area represents 68% of all the data values in the distribution. Okay, the next part of the rule says that 95% of the data values will lie within 2 standard deviations from the mean. So within 2 standard deviations means adding 2 standard deviations and subtracting 2 standard deviations. The range from here to here is 2 standard deviations, or is within 2 standard deviations of the mean. So what we have is the mean in the center. Subtracting 2 standard deviations brings us right here, and adding 2 standard deviations brings us here. And if we shade that area in, this reddish area represents 95% of all the data values. So 95% of all the data values in the distribution will lie within 2 standard deviations. So from x bar minus 2s to x bar plus 2s. And the third part of the rule, this is the final part of the rule, approximately all, which is 99 to 100% of the data values will lie within 3 standard deviations of the mean. So within 3 standard deviations, we have x bar plus 1, 2, 3 standard deviations, x bar minus 1, 2, 3 standard deviations. So from this edge to this edge, approximately all of the data values will be present. Okay, 99 to 100% of the data values. Now, it says 99 to 100% because there's still a possibility that you could have a data value that falls way above the rest of them or way below the rest of them. These, as we know, as we talked about earlier, are called outliers. The bell curve, you can see this little arrow here at the end indicates that this bell goes on forever towards the right and forever towards the left. Theoretically, the bell never touches the horizontal axis. And what that's allowing for are those potential outliers on the far left and the far right. Okay, so let's apply the empirical rule to a problem. The results of a standardized achievement test are approximately bell-shaped, with x bar equals 350 and s equals 85. So let's remember what we know about x bar. X bar is the mean of a sample, so we're working with a sample. S is the standard deviation for a sample, which is 85. According to the empirical rule, approximately what percentage of test scores would you expect to fall between 265 to 265 to 435, 180 to 520, or 95 to 605? Okay, so in order to apply the empirical rule in a problem, you must be told that the distribution is approximately bell-shaped. Okay, which we are being told here, so we can apply the empirical rule. To complete this answer, we're going to work from a blank bell curve basically, and we're going to label the horizontal axis. Then we're going to see if a test score equal to 625 would be considered an outlier. Okay, so we get started. This is a bell curve, and what we're going to do on the horizontal axis is start in the center with our mean. X bar equals 350. And then you're going to add a standard deviation. So if you take 350 and you add 85, 350 plus 85 is going, well, okay, here we go. We're going to take 350 minus 85 and get 265. That's going to be X bar minus S, and we'll label that right here. And then 350 plus 85 is X bar plus S, and we'll label that here. Okay, so we have 265 and then 435 with the mean in the center. We're going to do this for X bar plus 2S, X bar minus 2S, X bar plus 3S, and X bar minus 3S. So if you keep adding standard deviations, so 350 plus 85 is 435, add another 85 and add another 85, you can label the right hand side, and then you could take 265, subtract 85, subtract 85 again, and label the left hand side. So you get 180 when you subtract 350 minus 2 times 85, which is the same thing as taking 265 minus 85, and 350 plus 2 times 85, 350 plus 2s, is going to give you 520, which is the same as 435 plus 85. So 180, 520. And then X bar minus 3s to X bar plus 3s. 350 minus 3 times 85 is 95. You'll put that there. And 350 plus 3 times 85 is 605, and you put that there. Okay, so your horizontal axis is completed. There is a web work question just like this where you have to label the horizontal axis with the values for X bar minus 3s all the way to X bar plus 3s, and then answer questions on the empirical rule. Okay, so according to the empirical rule, approximately what percentage of test scores would you expect to fall between 265 to 435? So you look at where 265 falls, you look at where 435 falls, you take note of the area between 265 and 435, and by the empirical rule, this piece of area represents 68% of all data values. So the answer to this question is 68%, because 265 to 435 marks 1 standard deviation below the mean to 1 standard deviation above the mean. That's what we have right here, 1 standard deviation below to 1 standard deviation above. So the answer to that question was 68%. What percentage would fall between 180 to 520? So 180 to 520. By the empirical rule, this piece of area from 2 standard deviations below all the way up to 2 standard deviations above is 95% of the data. So the answer here is about 95%, since 180 to 520 marks 2 standard deviations below the mean to 2 standard deviations above the mean. So 95%. Okay, and the last part of the question, what percent would you expect to fall between 95 and 605? Okay, we're going to say 99 to 100%. Since 95 to 605 marks 3 standard deviations below the mean to 3 standard deviations above the mean. Okay, so that was the last part of the percentage questions, and then we have another question regarding an outlier. Would you consider a data value of 625 an outlier? Okay, well, look at where 605 is. If 625 were plotted on the horizontal axis, it would exist to the right of 605. Now that's outside of our 99%. Okay, so if there were a data score and its value were 625, it would fall over here to the right of 3 standard deviations. And we would say yes. 625 is an outlier since it lies far from the other test scores. According to the empirical rule, data values that lie more than 3 standard deviations from the mean occur less than 1% of the time. And so 625 is a very rare score. So by a rule here, we're going to say that any data value that falls more than 3 standard deviations above the mean, so more than x bar plus 3s, or less than 3 standard deviations below the mean, less than x bar minus 3s, any data that falls either there or there is going to be considered an outlier, a very rare score. Okay, we're going to further look at this empirical rule. 68% of the data values lie within 1 standard deviation of the mean. Okay, so this is 68% of our data values. Now, if we take a look at the bell curve, it is symmetrical with respect to this vertical line down the center. So if this whole piece represents 68%, we can divide the two halves into 34% and 34%. Okay, because we do have symmetry with the bell curve. So let's take it a little bit further. If we have 95% of the data values lying within 2 standard deviations of the mean, okay, so this represents 95% of the data values. Okay, let's see if we can figure out what piece of area this represents in terms of percentages and what piece of area this represents in terms of percentages. So you can figure it out if you take 95 minus 68 and then you divide that number by 2, you can get this area here and this area here. So if you take 95 minus 68, you'll get 27%. Dividing it by 2, 13.5 in this side on the left side and 13.5 on the right side. So if we add up 13.5, 34, 34, and 13.5, we'll get 95%. Okay, let's take it one step further. Approximately all 99 to 100% of the data values lie within 3 standard deviations of the mean. X bar minus 3s to x bar plus 3s. So all of it. For the purposes of this calculation, let's assume it's 100%. So let's figure out how much percentage lies in this far left tail and how much percentage of area lies in this far right tail. Well, if there's 95% of the data values falling between x bar minus 2s to x bar plus 2s, then the remaining 5% of area must be divided between the far left tail and the far right tail. So in each tail, we have half of 5%, which is 2.5%. So 2.5% in this tail and 2.5% in this tail. If we add up 2.5 plus 13.5 plus 34 plus 34 plus 13.5 plus 2.5, we're going to have a total of 100%. Okay. For a data distribution with a mean of 25 and a sample standard deviation of 3, what percent of data values A lie between 22 and 28, B lie between 22 and 31, C lie between 19 and 25? Okay, so we have our percentages marked: 34, 34, 13.5, 13.5, and 2.5, 2.5. If we label the horizontal axis using the mean of 25 and a standard deviation of 3, we'll get values 25, 28, because if we take 25 plus 3, we get 28, plus 3 is 31, plus 3 is 34. 25 minus 3 is 22, minus 3 is 19, minus 3 is 16. 22 to 28 gives us 34 plus 34, or 68% of the data values. 22 to 31, so 22 to 31, let's add up the percentages from here to here. We're going to add up 34 plus 34 plus 13.5, and that will give us 81.5. And the last one, 19 to 25%. We're adding up the percentages between 19 and 25, so we'll add up 13.5 and 34.5, and that's where you get 47.5%. Okay, measure